Welcome to tonight's video on Unit 3, Differentiability. When you get done with this video, you'll be able to determine where a function is differentiable. So differentiability means basically where you're allowed to take the derivative of a function. And a continuous function whose graph has no sharp turns is differentiable everywhere on its domain except at endpoints. All right, but here's an example of a continuous graph. So if you were to ask about continuity, you would say it's continuous everywhere because there's no holes, there's no asymptotes. It's just one continuous graph, and there's no sharp turns, so therefore it's also differentiable everywhere. Now below is an example of a continuous graph. This would be continuous everywhere. But notice there's a sharp turn here at 3. So therefore it would not be differentiable at 3. So therefore it's differentiable from negative infinity to positive 3, union 3 to infinity. Right? It's not differentiable at 3. Here there's 2 places where there's sharp turns, and those sharp turns would be where x squared minus 2 is equal to 0. So therefore those 2 sharp turns would be at plus or minus the square root of 2, this being negative square root of 2 and this being positive square root of 2. So it's continuous everywhere. However, it's differentiable on the interval from negative infinity to negative square root of 2, union negative square root of 2 to the square root of 2, union the square root of 2 to infinity. So these graphs are continuous on the domain, but they're not differentiable all throughout. All right. Now here's some graphs that are not continuous with no sharp turns. So notice they're continuous here on the interval from negative infinity to 6, union 6 to infinity, because notice there's a hole at 6. And it's also not differentiable at 6. So it's differentiable on the same interval, because the fact there's a hole there, it can't be differentiable. Here, there's a jump discontinuity at negative 4, so it's continuous from negative infinity to negative 4, union negative 4 to infinity, and it's also differentiable on the same interval. So basically, it would not be differentiable where it's not continuous. Another example of that is here there's an asymptote, so it's continuous on the interval from negative infinity to 3, and union 3 to infinity, and it's differentiable at the same interval, right? Because if it's not continuous at a point, then it's also not differentiable. Right? That's what this is saying here, that they're not continuous and therefore not differentiable at the places of discontinuity. So here's kind of a summary. If a function is differentiable at x equals c, then the function is continuous at that value. So differentiable means continuous. However, if it's continuous, it does not imply that it's differentiable. But if it's not continuous, it does imply that it's not differentiable. So that's what this is saying here. All right, so to understand this better, let's look at some graphs. And the first one, part A, f of x equals the absolute value of x plus 3. Is this continuous? And the answer is yes. One thing to keep in mind, this would be, if you look at the graph, right, this would be a v, at -3. One thing to keep in mind also is that an absolute value graph is a piecewise function. So if you put in numbers that make this positive, it stays the same. So if x plus 3 is greater than or equal to 0, then the value stays the same. Like when you take the absolute value of a positive number, it's that same number. If you take the absolute value of a negative number, then it's the opposite of that. So notice as a piecewise function, this is x plus 3 if x is greater than or equal to -3, and it's negative x minus 3 if x is less than -3. So that is how you can write an absolute value as a piecewise function. The reason why that's important is for part B, when it says to find the derivative. Well, notice derivative means slope. So the slope of this line here is 1. And the slope here of this line is -1. Now, the key is to know, is there a derivative at -3? And remember, a derivative is a limit, right? So the derivative from -3 to the left, which to the left is less than, so it's -1, must equal the derivative from the right, which is +1. So therefore, since they're not the same, it means f prime of -3 is equal to undefined, or does not exist. And graphically, what's happening is there is a sharp turn at x equals -3. So that's what it means when it's not differentiable. All right, we'll skip number 2. Number 3, all right, number 3, it says let f of x be equal to the square root of x. So remember, graphically, that looks like this. This is f of x equals the square root of x. And it says show all algebraic work to find the derivative of x equals 0. Well, note graphically, notice it's an endpoint, right? It's an endpoint. So therefore, if we find the derivative, remember we can use the alternative form and say the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. So that would be the limit as x approaches 0 of the square root of x minus 0, because if you put 0 in, it gives you 0, over x minus 0. So notice, if we put 0 in, that would give us 0 over 0. So this is the limit as x approaches 0 of the square root of x over x. So if we multiply, right, we get x over x rad x, which means it's going to be 1 over the square root of x. And if we put the 0 in, notice that means it goes towards infinity, which means that it does not exist. Now notice this matches up with graphically, because notice you have an endpoint there. So graphically, f prime of 0 is undefined or does not exist because 0 is the endpoint of the function. All right, so that's why graphically, whenever you see an endpoint, there is no derivative as well. So here it says, in order for a function to be differentiable at x equals c, f prime of c exists. For this to happen, the following statements must be true. F must be continuous at c. The derivative from the left must equal the derivative from the right, and the tangent line must not be vertical. So here, notice, in order to tell if it's continuous, remember you look at the changing point. There are 3 changing points here, -1, 0, and 2. So first we're going to determine if it's continuous. So remember the function value, f a -1. Well, notice there is no equal to, so it's undefined, which means that the function is not continuous at x equals -1, because remember, the 3 things that define continuity are that the function value exists, the limit exists, and the limit and the function value are the same. But if the function value does not exist, it's not continuous. And if it's not continuous, it's not differentiable at -1. So we can move on to 0. So at 0, f of 0, notice here's where it's equal to. So it's 0 plus 2, which is 2. So let's find the limit. So the limit as x approaches 0 from the left is right here. So that would be x squared plus x. It is 0 squared plus 0, which is 0. From the right, the limit as x approaches 0 from the right, that is x plus 2, which is 0 plus 2, which is 0, or 2, sorry. So the limit as x approaches 0 of this function does not exist because the limit from the left and right are not the same. Therefore, f of x is not continuous at x equals 0, and therefore it is not differentiable at x equals 0. So now x equals 2. So at 2, let's find f of 2. So f of 2 is 2 plus 2, which is 4. The limit as x approaches 2 from the left is right here. That would be x plus 2. So that's 2 plus 2, which is 4. The limit as x approaches 2 from the right. So from the right is when it's greater than. So that's x squared. 2 squared is 4 as well. So that means the limit as x approaches 2 of the function is 4. So that means f is continuous at x equals 2. So now we have to determine, is it differentiable? So remember, to determine if it's differentiable, we have to take the derivative from the left of 2. Well, from the left of 2 is right here. And notice this is a line, right? And the slope of the line is the number in front of the x. So f prime of 2 from the left is equal to 1. F prime of 2 from the right, well, from the right is x squared. So we can find the derivative by taking the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. Well, f of x is x squared f of 2 is 4. And notice if we put the 2 in, it would give us 0 over 0, which is indeterminate. So therefore, let's factor the x squared minus 4. So we get the limit as x approaches 2 of x plus 2. That is 2 plus 2, which is 4. So that means f prime of 2 from the right is 4. Therefore, f prime of 2 does not exist because the derivative from the left and right are not the same. So therefore, f is not differentiable at 2. So f would be continuous from negative infinity to negative 1, from negative 1 to 0, from 0 to 2, actually from 0 to infinity. It is continuous at 2. It's differentiable from negative infinity to negative 1, from negative 1 to 0, from 0 to 2, and from 2 to infinity. All right, good stuff. All right, drawing some sketches that tell you f prime of 2 equals 0. Remember, 0 means it's a horizontal tangent line. So if you have the vertex of a parabola at 2, right, this would be a sketch of a function where f prime of 2 would equal 0. All right, the next one, notice here, it says use the graph provided to complete the following. State where f of x is undefined. Well, if you look at undefined, that would be at C. And that's it. Everywhere else, f of x is defined. Part B, it says state where f of x is not continuous. Well, at C, there's a hole. At F, it's broken up. And that's it. Now, part C says where is f of x not differentiable? Well, remember, it's not differentiable if it's not continuous. So at C is 1, at F is another. Also some sharp turns, like G and N, right? Because those are sharp turns. Otherwise, it's differentiable everywhere else. So C, F, G, and N. So part D says the intervals of continuity. Well, it's continuous from negative infinity to C, from C to F, from F to infinity. Part E says state the intervals of differentiability. Well, differentiability is where it's continuous and it doesn't have a sharp turn. So it'd be from negative infinity to C, C to F, F to G, and then from G to N, and from N to infinity. That's where it's differentiable. Now for part F, it says, well, actually for part, it says, are D and E equivalent? And the answer is no, right? There's a couple, there's an different interval there. So G wants to know, state the intervals where the derivative is 0, greater than 0. Meaning, where is the slope positive? Well, notice the slope is positive, right, all the way here until B. So it's negative infinity to b, and then the slope goes down, then it's 0, then it goes up from g to h, and then it goes up from n to o. That's where the derivative would be positive because the slope of the line is positive. Now for h, it says where is the slope negative, and the slope is negative from b to c, from c to e, and then it's negative from h to n, and then from o to infinity. And notice this is where the graph is going down from left to right. Where is the derivative 0? It's at basically the top of the parabola at b. The slope is also 0 from e to f. It's also from f to g. And then it's at h. And that's it. That's where the slope is 0. All right. Then for the next ones, it says state the values where the function is potentially not differentiable. And so when you're talking about potentially not differentiable, remember, think of absolute value as a piecewise function. So here, it's going to be x minus 2 if x minus 2 is greater than or equal to 0. And we'll put the minus 3 out here for now. Then it's going to be the opposite of x minus 2 if x minus 2 is less than 0. So this is x minus 2 if x is greater than or equal to 2. Negative x plus 2 if x is less than 2. Then you subtract 3. So you get x minus 5 if x is greater than or equal to 2. Negative x minus 1 if x is less than 2. So that's the piecewise function that goes with this absolute value. So the changing point is 2, so that's where it is. So here the changing point is 2, so it's potentially not differentiable at x equals 2. So determine if the function is differentiable at the values. So remember, let's figure out first here what's the derivative of this. So remember the slope here would be 1 if x is greater than 2, and it'd be negative 1 if x is less than 2. But let's determine if it's actually differentiable at 2. So remember f prime of 2 from the left is less than, that would be negative 1. F prime of 2 from the right is 1, so therefore f prime of 2 does not exist. So therefore we leave it with no equal to, right? So therefore f is not differentiable at x equals 2. So for part C, it says the interval of continuity. Well, it's an absolute value, so it's a continuous everywhere. Right? All absolute values are going to be continuous, but it's differentiable only from negative infinity to 2, union 2 to infinity. All right, the next one, right? We see that it's a piecewise function. So notice the changing point is 2. So part A, it's potentially not differentiable at 2. All right, for part B, all right, now for part B, here's something you keep in mind. In order for it to be differentiable, right, it has to be continuous. Well, this is not continuous at 2 because if you think about it, f of 2 is undefined, right? So therefore, it's not continuous at x equals 2 and therefore not differentiable. So for part C, we say it's continuous from negative infinity to 2, union 2 to infinity, and it's also differentiable on the same interval. All right, so number 6 is the same problem, except now it says equal to 2. So we'll evaluate at 2 for potential not differentiable. But now we know that it could be continuous because f of 2, the square root of 2 times 2, is 2, because the square root of 4 is 2. The limit as x approaches 2 from the left, well, from the left, it would be 1/2 x plus 1, which is 1/2 1/2 times 2 plus 1, which is 2. The limit as x approaches 2 from the right is the square root of 2x, which is the square root of 2 times 2, which is the square root of 4 is 2. So that means the limit as x approaches 2 of h of x is 2. So therefore, since the function value and the limit are the same, this is actually h of 2, not f of 2. We'll make that an h. It's h there. So therefore, h is continuous at x equals 2. So now we have to determine if it's differentiable, right? So if we take the derivative here, well, the derivative of this part is just 1/2 because that's the slope. Now the derivative of the square root of 2x, so if we take the derivative, remember, the derivative is equal to the limit as h approaches 0 of f, we'll call it f prime of x, just to make it different. F of x plus h minus f of x all over h, that gives us the equation of the derivative. So if we put x plus h in there, we get the limit as h approaches 0 of the square root of 2 times x plus h minus the square root of 2x all over h. So now it's going to be the square root of 2x plus 2h minus the square root of 2x all over h. So if we put 0 in for h, notice we would get 0 over 0. So in order to simplify, we have to multiply by the conjugate. So we multiply by the conjugate. When we do so here, we get 2x plus 2h minus 2x all over h times the square root of 2x plus 2h plus the square root of 2x. So notice the 2x's cancel, and then the h's will cancel. So you have the limit as h approaches 0 of 2 over the square root of 2x plus 2h plus the square root of 2x. So then when you put the 0 in for h, you get 2 over 2 times the square root of 2x, which simplifies to 1 over the square root of 2x. So that is the derivative there. Now, to see if the derivative exists at 2, we'll do h prime of 2 from the left. That's equal to 1/2 h prime of 2 from the right. So 1 over the square root of 2 times 2. That's 1/2 as well. So notice h prime of 2 would equal 1/2. So therefore, it is differentiable at 2. So when we talk about part C, it's continuous from negative infinity to infinity, and it's also differentiable everywhere. Okay, the next question. So here it's a cube root. So notice a cube root of x minus 2. The cube root graph, if you look, would look something like this. So the point that you want to check is where it changes, like kind of the middle of the snake here. So we're going to check x equals 2. That's the point that makes it equal 0. So for a cube root graph, it's continuous at x equals 2. But now to show, because remember it says for part B, to determine if it's differentiable, right? So if we want to find j prime of x, in this case j prime of 2, we could do the limits as x approaches 2 of the cube root of x minus 2 minus 0 over x minus 2. So we would have the limit as x approaches 2 of the cube root of x minus 2 over x minus 2. So if you think about this, the best way to simplify this is to think about this as exponents. This is the same as saying the cube root of x minus 2 is the same as saying x minus 2 to the 1/3 power. And this is x minus 2 to the first. Remember, if you have the same thing and you're dividing, you can subtract the exponents. So this would be the limit as x approaches 2 of x minus 2 to the negative 2/3, right? Because basically 1/3 minus 1 is negative 2/3. So it's the limit as x approaches 2 of 1 over x minus 2 to the 2/3. And if you put the 2 in, it would be 1 over 0, which goes to infinity, which means it does not exist, right? It does not exist. So therefore, j prime of 2 does not exist. So therefore, j is not differentiable at x equals 2. So if you think about for part C, it's continuous everywhere, but it's differentiable only from negative infinity to 2 and from 2 to infinity. And last but not least, it says k of x equals 3t, right? Well, if this is x and that's t, that means 3t is a constant. So basically there's no potential place where it's not differentiable. Since this is a constant, that means it's a horizontal line, which means it's going to be differentiable and continuous everywhere. All right, I hope you enjoyed the video, and if you have any questions, please feel free to ask in class. Have a good rest of your evening.